So in this second part, we'll continue with the optical characterization basics. In the last class, we know that if we consider any kind of electromagnetic radiation, specifically the IR or the UV visible radiation interacting with matter, it can basically be absorbed, transmitted, or reflected. We are going to look more into this aspect in today's class. So if we consider something as absorption, it is actually the property of the material, okay, of transferring energy from the photon to its atom and molecules. So we have got the photons of energy, let's say h nu. When it actually interacts with the matter, the chances are that some part of it gets absorbed or the entire part of it gets absorbed. Now where does that energy goes? That energy usually goes into the atoms and the molecules of the system we are considering. So let's say, for example, you want to study some kind of nanomaterial and you see that a part of it or the part of the incident radiation is getting absorbed. That will actually give a lot of information about the system. So the ratio of the energy transferred to the matter from the incident light to the total incident energy is called absorbance. So you basically have a term, okay, this should be absorbance, okay, it's not absorptance, okay, or we can actually call it that also. But what happens is usually if we have the ratio of the energy transferred to the matter from the incident light, okay, so how much energy is transferred to the matter to how much energy is incident on the matter is something which is denoted as A. So this can actually be termed in terms of the reflection and transmittance. What happens is if a radiation is incident on a particular sample, a part of it is absorbed, a part of it is transmitted, and a part of it is reflected. So if you add all of them, so if you add absorbance plus transmittance plus reflectance, we basically get something which is the total. So that's total is taken as 1. Okay. So if we just want to get the absorbance, we'll take the reflectance and the transmittance on the other side, and we actually get these kind of relations. So this is a very simple concept. Okay. The coefficient of absorption is the rate at which the light is absorbed when traveling through the material. So how fast the light is absorbed in the material is something which we call as the coefficient of absorption. So coefficient of absorption is a very important term. Okay. And then this coefficient of absorbance A is given by absorbance divided by the length of the path through which the light usually travels. You can also write it down in terms of the log scale in terms of transmittance. So what happens is you usually can replace all the terms, okay, and then you can actually find out different forms of it, okay, using these two relations. But for now, I'd like to tell you that L is a very important part, because L is the length of the path traveled through the material. And then it's quite obvious, if the length is more, then the absorbance will more or less be there. Okay. So if there is more length, okay, the coefficient of absorption is definitely going to get affected, because there is going to be more and more absorption as such. Okay. So if you consider the light scattering technique, the light scattering may be either elastic in nature or inelastic in nature. I think in the last few lectures we also have discussed about elastic and inelastic scattering. When we talk about elastic scattering, it simply means that more or less the energy is conserved, whatever is incident, that is actually coming out of the system. But when we consider inelastic scattering, some energy is lost into the system. So if you consider an elastic scattering, the term you might have heard is called Rayleigh scattering. There is one more scattering which is the Meese scattering. Now Rayleigh scattering and Meese scattering actually depends, the definition is usually more or less the same, but it actually depends specifically on the size of the scatterer. And on the other hand, if you consider something like inelastic scattering, we have got the Raman scattering and Brillouin scattering. The reason here we can talk about is something like the responsible for the color of the blue sky, as well as for the yellow and the red orange tones of the sunrise and the sunset. Okay. So this was actually a Rayleigh scattering part, sorry, not the Raman scattering part. So Rayleigh scattering part. Now this was actually studied and established, okay, long back, based on this intensity and the incident wavelength, or the wavelength that is being scattered, depending on those factors. So what happened was Lord Rayleigh was the first to establish a quantitative theory for the elastic scattering of light by particles whose diameter d is small compared to the wavelength of the light. So, the particle might have a diameter d, and that diameter, if is small compared to the wavelength of the light, this usually gives rise to something which we call as the Rayleigh scattering, which is a elastic scattering in nature. And if you look into the relation, we have got this expression here, where I is the intensity of the light scattered by the dipole induced by the light on those particles, okay, with a volume V. So, we have got a particle, we have got a system which has got a volume V, and there is a light of intensity I incident on it, and R is the distance to the particle, okay. R is how much distance the light actually travels before it interacts with the particle, and M is the relative index of refraction or refractive index. So, this is the relative refractive index. This basically the refractive index will depend on the surrounding medium and of course the particle. So, this is an expression that is important for Rayleigh scattering. And then if we actually look into the appearance of the blue sky, if you look into this particular relation, you see that this is the wavelength here. So, if the wavelength is more, the intensity would basically be less, right. So, this is inversely proportional. So, what happens is light with shorter wavelength is scattered much more efficiently, okay. Thus, why we see the sky blue during the day. So, if the physics says that if the wavelength is short, so if we reduce the wavelength, okay, the scattering would be more or less efficient, okay, much more efficient, and that is why a larger particles scatter the light without a strong dependency on the wavelength. Thus, the color of the clouds becomes white. So, color of the sky becomes blue because we have got blue on the shorter wavelength region, and if it is shorter, it is scattered more efficiently, and hence the sky appears blue. On the other hand, why does the cloud appears white? Because the cloud has got a larger particle scatterer, okay, and it usually does not depend on the wavelength. So, if it does not depend on the wavelength, the scattering will be of all the different colors, and when the 7 different colors we have, we basically have nothing but the white color. So, as a result, the cloud will actually appear white in color. So, this scattering of the light by larger particles is generally called Mie scattering. So, this cloud is more or less related to Mie scattering and not Rayleigh scattering. On the other hand, if we consider the sky appearing of the sky as blue, it is basically connected with the Rayleigh scattering, because Rayleigh scattering is used for scattering of smaller particles. So, how large the particle should be, so that we can actually refer it to the Mie scattering? It should be 1/3 of the wavelength or even larger than that, okay. So, that is important. And then let us go for inelastic scattering, or we basically call as the Raman or the brilliant scattering. Now, Raman effect is something which is very much studied, okay. It is basically an optical phenomenon. So, what happens is photons incident on a molecule can also excite normal modes of vibration of that molecule or photons in a solid. So, if you consider the modes of vibration, okay, in a solid, we basically have something which we call as the normal modes of vibration, okay, if you consider just the molecule part, okay. So, likewise what happens is it can be scattered by phonons in the material. So, we have got the phonon vibration, and these photons can be scattered by the phonons, and it will usually gain the energy corresponding to those phonons. So, it will actually gain an energy corresponding to those phonons, and this inelastic scattering is known as the Raman scattering when optical photons are involved. So, we have studied about phonons, photons, excitons and so on. You can refer to that in the last lecture. So, Raman scattering is when optical phonons are involved. On the other hand, if we consider brilliant scattering, it basically takes the acoustic mode which is responsible for scattering. So, there are two modes of vibration of a molecule. One is the normal mode of vibration and one is the acoustic mode of vibration. So, when we talk about the normal modes of vibration and we are talking about the optical phonons getting involved, we talk about the Raman scattering. On the other hand, if we consider the acoustic mode of vibration, we are talking more or less about the brilliant scattering. So, that is the difference. So that might be a 2 marks question, because we can ask what is the difference between Raman scattering and brilliant scattering, or Rayleigh scattering and Mie scattering, and so on. Okay. So the photons emerging from the interaction, so we are talking about Raman effect here. So if we have got the photons which are getting emerged from the interaction, might have a low energy than that of the incident photon. So if the energy is low, that means the wavelength is on the larger side, right, because energy and wavelength are inversely proportional. And then if we consider something as low energy, that means some kind of energy has been given to the system. We basically call it the interaction, which is the Stokes scattering, and the term anti-Stokes scattering is used otherwise. Okay. So it might happen that within the system the incident photon will actually gain some kind of energy, and it will result in a higher energy exit. Okay, that will actually refer to anti-Stokes scattering. So since the allowed modes of vibration of a solid or a molecule are intimately likely linked to its structure and the chemical composition, so whether you get a Stokes scattering or an anti-Stokes scattering will totally depend on the structure and the chemical composition of the material. So this inelastic light scattering can be efficiently used as a structural characterization method and as a substance detection and identification tool, and that is why Raman studies are done. So Raman studies is usually done for this. Okay. So Raman studies can be conducted, and we can look into the Stokes scattering and the anti-Stokes scattering and comment on the structure and the chemical composition of the material. So if you look into one of the most common technique of spectrophotometry, this is nothing but the UV visible and near infrared spectroscopy. And what happens is we have got the radiations involved here, which lies in the UV range or the visible range or the near infrared range. So the basic method to investigate the property of any material through their interaction with light, and to measure how much light is reflected, transmitted or absorbed by that material. So we usually study these three things. More or less, if we know one factor, the other two factors can be determined. Okay, it is also possible. Okay, from the formulas that we have mentioned before. So if we measure that absorption as a function of photon energy, so if we say how much absorption has occurred in terms of photon energy, because the incident light or the radiation is nothing but photons. So how much energy has been absorbed within the system, we can actually comment on the electronic. Okay, so we can usually comment on the electronic and the atomic structure of the material. And then if we look into spectrophotometry, it is one of the most widely used confirmation technique, and also to have an in-depth analysis of the material. And then basically it measures the intensity of transmitted and the reflected light. And if you look into a typical spectral range covered by high-end commercial device, it will basically range from the near infrared region, ultraviolet region, that means around 200 nanometer, to the near infrared region, that is up to 3 micrometer. So it basically starts from 200 nanometer, then it goes to the visible range, which is 400 to 700 nanometer, and then it crosses that and goes up to as high as 3000 4000 nanometer, which actually lies in the far infrared or to the near infrared regions. Okay, so that means that it can be actually used for a wide range of radiation spectra. And then UV visible is usually used to designate spectrophotometry, the technique. So basically we call spectrophotometry, which is the technique, and spectrophotometer is the name of the instrument. So the technique is spectrophotometry and the instrument is spectrophotometer. So that's all for today. In the next lecture we are going to continue with some more basics of optical properties.